Alright, welcome back to another video. Now we're going to be talking about the actual components, the fundamental components of the electrocardiogram. Alright, so we're going to be talking about waves, right, segments, and intervals. But first, we're going to have to speak a little bit about cardiac electrophysiology, right? So we have alluded to it before. You have your atria and your ventricles, right? Okay, so SA node depolarization results in atrial depolarization, right? And atrial depolarization can be sensed, or what's another word I want to use? Not picked up, yes, but it can be perceived, right? So atrial depolarization can be perceived on the 12-lead ECG. Not sinus node depolarization, but the depolarization of the entire cardiac tissue, which is the atrium. All right, cool. So after atrial depolarization, right, the impulse is held briefly in the AV node, right? And there's a physiological reason for this. Essentially, it gives the ventricles time to fill, right? So after atrial contraction, it gives the ventricles a little bit of time to fill up before the ventricles contract, right? So anyway, the impulse is held briefly in the AV node, right? And that it is transmitted via specialized conducting tissue to the ventricles, right? So AV node activity is not visible on the ECG, right? So the electrical activity of the AV node is not visible on the ECG. However, because the ECG is a diagram of voltage versus time, the time it takes for the impulse to be transmitted into the ventricles is reflected on the ECG. Okay, and then the QRS complex, or rather the ventricular activation, so the activation of the entire ventricle, right, will be reflected on the ECG also, right? So in summary, as we have alluded to before, large masses of tissue can be picked up on the surface electrocardiogram, right? So both atria as one, both ventricles as one, right? But smaller areas are not reliably illustrated or picked up on the ECG. Okay, so that's the first basic concept I want to teach you. Okay, so now we have spoken, so let's go in sequence now. So you have atrial depolarization, right? AV node delay, ventricular repolarization. Okay, now there are two other actions that I would include in this diagram. You have depolarization, rather. You have ventricular repolarization, and you have atrial repolarization. Okay. So early on, I'd like to say that atrial repolarization is not reliably seen on the ECG for two reasons. If this, again, is the heart, you can see that the ventricular tissue is much larger than the atrial tissue. Okay, and due to this, right, when the atrium is repolarizing, it tends to be obscured by the vector caused by ventricular depolarization. Because remember, we said that what the ECG is picking up is mean electrical vectors. So even if the atrium is doing one thing, if the ventricle is doing another, or if the ventricles are doing another thing, and the ventricles are a large mass of tissue, then the activity of the ventricles will supersede or have a greater impact on the mean electrical vector, and that's what will be reflected on the ECG. In addition to that, atrial depolarization is more gradual and takes a little bit longer than atrial depolarization, so you have a smoother wave. So if this is atrial depolarization, you may end up having something like this, or atrial repolarization. So it may be very difficult to distinguish atrial repolarization from the isometric baseline of the ECG. Okay, so for all intents and purposes, we don't really analyze atrial repolarization on the ECG. This is an oversimplification, but it holds true in most situations, right? Now, there is something else that I need to explain that is a little bit counterintuitive, right? Okay. Usually, if depolarization goes this way, right, and results in a positive wave, repolarization going in the same direction is actually an opposite electrical phenomenon and should result in a negative wave, right? So what we're saying is, for example, if this is just an example, or it's a conceptual illustration. I'm not making any effort to be 100% accurate in terms of the types of electrical charges that are moving, right? But let us say if repolarization results in a movement of positive charge, if depolarization results in a movement of positive charge in this direction, then repolarization would